Hi everybody. So up to this point we have assembled the board. We reviewed the schematic and kind of talked about the theory of how it works. We applied voltage to it and did some voltage measurements and kind of recorded that. And then we applied a signal to the amplifier and played some music through it and listened to it, and just as it is. And then finally we went through with the oscilloscope and we viewed some of the waveforms, and we kind of got a little deeper into how the differential input pair works and how the negative feedback loop works in one of these amplifiers. So now what we're going to do is this is still all stock. Nothing has been modified in this amplifier. So what I'm going to do is I'm printed out a little form that I made, and all I'm going to do is measure all of these parameters and record them so we know what the amp looks like before we modified it. The following videos that will come after this one are going to involve actually making modifications to the amp in steps. We're going to do it step by step, and then finally when we're done doing all of that, we'll come back to this form and we'll record our results after everything's all done. Now, as I said before, this power transformer is too large for this amplifier, and it will exceed really the safe operating range not only of the transistors but of the filter capacitors and so forth. So what I had to do was I used the variac in the electronic circuit breaker to limit the voltage into this transformer and get it down to where we need it to be. So I have it set pretty much to put 18 volts, times 2, of course, for our positive and negative supply, 18 volts RMS AC. So we're going to turn this on, and you can see the input right now is only about 102, 103 volts, something like that. And it does move around here at the house. So my input voltage right now is 120. Earlier in the day it was up to like 124, I think, 122. So it'll vary a little bit. And you can see the idle current, and this is the AC current going into the transformer, is only about 96 milliamps. And that's what the amplifier turned on. Now the first thing I want to do is move my camera a little bit, and we're going to check our voltage coming from the transformer. So from one side to the center tap is 17.67, and to the other side should be about the same, 17.6 or 17.7. So what I'm going to do is I'm going to just bring this up a little bit till I get right on that 18 volt mark. There we go. That's pretty good. So there's 18 volts, and that's going to be 36 volts center tapped. And there it is. Looks good. Now the next thing I want to do is I want to take a couple of measurements. So we're going to first of all write down our 18 volts. Okay, now that that's written down, we'll switch to DC volts. And we're going to measure our B+. That's the easiest one to get to right now, because we can just touch this heatsink and B+ is going to be right there. So this is our rectified DC voltage, and you can see it's 24 volts, 24.1. So we have plus 24.1, and then B-. Looking at the schematic, we should be able to get on this R25. So where R19 and 25 or 20 and 26 go together. There, negative 24.2. Now next thing we want to measure is DC offset on our speaker terminals, and I do have speakers connected. Typically you would measure it with no speakers connected, because that's the worst case scenario, but I'm too lazy to disconnect it, and I think this will still give us a good idea. And if I go across the terminals, I have 65 millivolts. I'm just going to call that 65. It bounces around. So left channel is 65 millivolts and right channel is 73 millivolts. See that? So we have 73. Okay, now I have 50 millivolts RMS set to go to the input of this amplifier, and I'm going to measure it right here where it's going into R1 or R2. And I just want to make sure, because you're going to have a little bit of loss, and I just want to see exactly how many millivolts is going into this. So I'm going to try to precariously hold these probes from R2 to ground. If I can reach around the camera, turn this on, you can see 49.4. And of course, I just have them tied together so they're both getting 49.4 millivolts. So that's almost exactly 50 millivolts, pretty close. And to measure it with a meter like this, you have to have a meter that can measure AC voltage at 1 kilohertz accurately. And that doesn't necessarily mean true RMS. True RMS is something different. True RMS is the ability to measure a non-sinusoidal waveform and get the actual RMS value. But true RMS has nothing to do with the maximum frequency that it can measure accurately, if that makes sense. So this meter can measure a 1 kilohertz sine wave accurately for its amplitude. And you just saw that on there. So that's our input. Okay, the next thing I want to measure is with that 50 millivolts input, I want to see how many volts RMS output I'm going to get. And this meter reads directly RMS voltage. So I want to measure that right into the load, and we're going into an 8 ohm load. That's important because when we're going to calculate the actual wattage, that's going to come into play. So we're looking at RMS voltage across an 8 ohm resistive load. So let me turn that on, and I just have the meter connected right now. And you can see I have about 3.37 volts on the left channel. Okay, so 3.37. And then if we move over to the other channel, this will be right channel. Should be about the same. And it's 3.4. Now we've already learned something right now, a couple of things. Number one, we know that with the same input signal, both channels are outputting almost the same output level. So the gain of channel A and channel B, or left and right channel, is almost identical. That's great. So now let's do a few calculations. Okay, to calculate the wattage, you take your RMS voltage into the 8 ohm load, you square it, so 3.37 squared, and then you divide that by your load resistance, which would be 8 ohms. So 3.37 squared divided by 8 would equal 1.42 watts. So we're putting 1.42 watts into the resistors with this 50 millivolt input, let's say. And if you take that output voltage divided by the input voltage, that's going to give you your gain, your forward voltage gain. So this amplifier has a forward gain of about 68, which for this type of amplifier is pretty high. I mean, that's a pretty good, relatively good gain. Now the next test we want to do on this amplifier is THD, or total harmonic distortion. I get a lot of comments about this that I think everybody kind of knows what distortion is, but they don't know what distortion is, and they kind of ask questions. So let's talk about it a little bit. The test that we do is you apply a pure sine wave into the amplifier. That pure sine wave passes through the amplifier and it gets amplified, and it comes out at a higher amplitude and higher current capacity at your speaker terminals. Now what happens between this input here and this output here should be just amplification only. It shouldn't modify the waveform in any way. It shouldn't change it, just make it louder. Any frequencies that come out that are not that pure sine wave, that fundamental frequency or fundamental anything, whether it be, you know, a complex waveform, whatever, anything that's different from the input is considered distortion. Now, harmonic distortion is the type of distortion where you get something that's not your fundamental frequency, and it will be a harmonic of that frequency. So for instance, if I put a 1 kilohertz signal into here, a harmonic of 1 kilohertz would be 2 kilohertz and 3 kilohertz and 4 kilohertz. Every multiple of that frequency is considered a harmonic. And of course, there are even harmonics. So you have the second harmonic, third harmonic, fourth harmonic, the second, the fourth, and so forth. Those are even harmonics. The third, the fifth, the seventh, and so forth. Those are the odd harmonics. And each one can be produced by different things happening in the amplifier, to make a long story short. Now, a lot of things can cause that to happen, to distort the waveform. And really, you will see harmonics when that sine wave is no longer a perfect sinusoid. In other words, when it kinks, or when you get some sort of anomaly in that waveform somewhere, that's what will make that waveform produce harmonics of itself, if that makes sense. Now, I get a lot of questions about the distortion meter, and this is a Keithley Model 2015, but there's also analog distortion meters like this one up here that you see. I don't use that a whole lot because it's manual. You have to turn a bunch of knobs and so forth. This one's automatic. It's a lot easier to deal with. But all these they're a fancy AC voltmeter with some filters in it. So what it can do is, this meter, since it has an automatic mode, it can determine the fundamental frequency. So it'll look at the highest amplitude frequency in whatever's coming into its input. In this case, if we use a 1 kilohertz tone, it will identify 1 kilohertz as its fundamental frequency. It then uses those filters to filter out everything that is not a 1 kilohertz signal. So that gives you the amplitude of that 1 kilohertz. Then it measures the overall signal and subtracts the two. The difference between the two is the distortion. Now this one can go a step further because it can actually filter individual harmonics. Like I can have it only look at the first, the second harmonic or the third harmonic and ignore all the ones above that. Or I could have it look at, out however many harmonics I want. I can also put weighting into it. I'm not going to talk about what weighting is, but it's distortion that is more close, or how do I put it, more close? Closer to how your ear works, how your ear hears the sound. It's math that it applies to it. So really the main thing you need to know is anything that is not your 1 kilohertz signal in this case is distortion. The percent distortion, or total harmonic distortion, is the percentage of that total signal that is not 1 kilohertz. So anything that's not 1 kilohertz adds into this percentage. So the more of those, the higher the amplitude and the more of those harmonics that are in there, the higher this percentage will get. Now you notice right now it says about 0.01% or 1/100th of a percent THD. And what you're looking at is that 50 millivolt RMS signal coming directly out of the signal generator and into this. So the signal generator's internal distortion, the distortion caused by this cable and the connectors and everything, and yes, those can cause problems. Those can add distortion because they could add noise to the signal, which will modulate that 1 kilohertz and make harmonics out of it. And the internal limitation of the meter itself. So all that combined, our baseline is 0.01% THD. So that means that no matter how clean this amp is, the minimum that we could ever read coming out of that amp will be 0.01% theoretically. You'll never see that, but that's theoretical. So that's what we're looking at. So we can guarantee that anything that comes out of this amp will be above 0.01. And if this is the exact output at the speaker terminals, then you have a one-of-a-kind amplifier, because basically that means the amp is putting absolutely no distortion into the signal whatsoever. Okay, as you can see, I have the speaker dummy load connected, and I also have this jumper that goes over to the input of our distortion meter. And I'm going to turn on our input signal of 50 millivolts and get our 3.37 volts out. And let's see how much of that signal is distortion. And you can see right there, this amplifier has 0.13% total harmonic distortion. And if you subtracted that 0.1, it's actually about 0.12% distortion. But we're going to just write it as is, so we don't have confusion. So the left channel is 0.12, let's say 125%. Okay, moving our probes over to this channel. Turning the signal on, and you can see it's almost identical. 0.1, about 0.127. So that's actually not a bad number for this type of design of an amplifier. If you look at any of the commercially built low power amps, that are the, like the Pioneer, 424, 425, 535, SX450. You look at the little Marantz, was it the 2215 and some of those, they're all going to have just under 0.1% distortion, somewhere around there. So it's anything getting much above 0.1%, you can sometimes start to hear it, but you really don't hear harmonic distortion until it's up closer to 1%. So when you hit that 1%, that's when it starts, you can start to notice it. It may not be totally annoying, but you'll notice it. It won't sound as clear as, when you're below 1%. So again, not too bad. Okay, the next thing we're going to do is just our linearity sweep test. This is kind of subjective, but what I'm going to do is just see how much it varies. So if you have a total, we know that our maximum, our average signal is going to be about 3.3 volts. And I just want to see, and that's RMS, by the way. And I just want to see how much that translates to in 10 hertz versus 48 kilohertz. And again, I'm going way beyond. Okay, so 20 kilohertz, I'm going double that. So let's do that. Now you can see I have both channels connected right now. And this is the left channel, this is the right channel. I'm at 5 volts per division, so each one of these little notches is 1 volt. And that would be peak to peak, of course, if we look at when this opens and closes. But each one of those represents 1 volt. So let's turn this on. You can see right now, when it starts, it's just barely over 10 volts, peak to peak. And when it's up to its maximum frequency, it drops just to about 9.5. So let's say it's going from 10.5 to 9.5. So it's moving approximately 1 volt. And both sides are breathing in and out, so that would be 1 volt peak. So it's moving about 1 volt peak from lowest frequency to highest frequency. So accounting for peak versus RMS, and of course peak is half of peak to peak, we're looking at about 0.7 volts. Okay, what I'm going to do here, we're looking at the left channel, and the right's going to do the same thing pretty much. So I'm going to turn on my signal like this, get this back to where we have a couple of waveforms on here, right? And then I'm going to go from a sine wave to a square wave. See that? And I'm going to go to DC coupling, and you can see it's pretty square. There's a little bit of drop at the top, and that's probably because of our power supply. You can still see that notch distortion right there, but there's your square wave. It's pretty clean. That's not too bad, believe it or not. Now what we're going to do is we're going to introduce an active load to this. So what we're going to do is we're going to take, this is a 470 nanofarad capacitor, or about a half a microfarad. And I'm just going to put it right across the speaker terminals, because cheap amplifiers just like to go into oscillation when you put this capacitor on here. So you can see it's clipped right across the leads. And we'll turn this on. And you can see right there is just a little bit of ringing. See there? It's not too bad, really. Not hardly any at all. Very good, and it controls it very, very quickly. Nice. And part of that has to do with the design of this amplifier, and part of it has to do with this little network here called a Zobel network. Now, when you use a Zobel network, filter network, in this capacity on a speaker, sometimes some people will refer to it as a Bouguereau cell. It doesn't matter what you call it. It's still a form of Zobel network, and all it is a resistor and a capacitor setting up kind of an RC time constant. And what this is going to do is this is going to filter out that high frequency oscillation, but it's not going to have any influence on low frequency or audio frequencies. And that's what's there. Now sometimes they'll add an additional network of a inductor wrapped, it'll be a coil of wire wrapped around a big power resistor. And they'll put that right in series here, but as you can see, we really don't need it on this amplifier. It's working pretty good. Now, last but not least, we'll test this for maximum power. And we'll go to 2 channels again. Actually, I'm just going to put them over top of one another, and they should both track pretty close. All right. Let's turn this on. And I'm going to have to go down a couple of notches here. And we're going to take this up to maximum power till it clips, and then we're going to just measure our RMS voltage. And the way I'm going to do that is I'm just going to put my voltmeter on there and measure the AC RMS voltage. Okay. And let's go up, and we're just going to take it right up until it clips. I'll hold this right here. Hopefully we're all in shot. And I really don't care what my input is. So right there is clipping. There's just below clipping. You can barely see a little bit of clip right there. And I have 13.3 volts AC. Okay, turn this on. 13.3 volts squared divided by 8. 22 watts per channel. So this amplifier can produce 22 watts per channel. So I'll just write that down here too. And you can see at that 22 watts per channel, we're edging right about 0.3% total harmonic distortion. So there's a wee little bit of distortion in there, but it's still not horrible at full power. And these are getting warm, but they're not burning your hand or anything like that. They're not too bad. And just to see how this electronic circuit breaker works, I'll give you an example. So I have this turned on, and I have the trip point set so that when we overdrive it too much, it'll shut the amp off. And watch, and you can listen, you'll hear a clunk as I go up. I'm getting pretty good into clipping now. Boom. And that's what it's supposed to do. So if something goes wrong while we were doing that test, that we draw more than the amount of current we're supposed to, it just kills the power. And you can see it shut it right off. And then I can reset it, and we're back on. Okay, the last thing I want to address here is, you may or may not be able to see it. I think you can. If you look right here and here and here and here, you see a little bump in the waveform. If I just go to one channel here, I can stretch it out a little more. And you can see right here, this is the zero crossing right here. So this is where the sine wave goes from positive going to negative going. I can slide this over a little bit. And you see right there, that little notch. That is called crossover distortion. You've heard me talk about that a lot in the past. Let's turn this off, I'll show you. And let's go to the schematic. So what's happening is, you see these two transistors right here. And we have that bias voltage here. And some of you are already screaming at the camera, but we're not going to spoil it for everybody here, because we're going to do this systematically. But what's happening is, this transistor, when you're coming from that positive going, so remember we saw that kind of positive, that waveform. We saw that waveform on the scope, and what's happening is this transistor is handling this part of the waveform from 0 volts up to the peak down to 0 volts. This transistor is handling the negative part. And what's happening is, just before we get to 0 volts, this transistor is turning off. It's no longer conducting. And that's because the voltage on your driver is dropping below the forward voltage drop. You got to have at least that 0.7 volts or whatever it takes to turn this transistor on, or the transistor will just shut off totally. And that's what's happening, is this is shutting off before your signal finishes getting all the way to its 0 point. Then, after it sweeps through that, this transistor will finally turn on and pick back up and continue. So that little notch is that little area where neither of the transistors is turned on, and that's called crossover distortion, because it's when you're crossing over from this transistor to this transistor, from the positive to the negative polarity. And, well, the reason for that is that these don't have enough voltage during idle to stay on when you're going through that crossover. There is a point at which one of them is still working, but the other one is not, and there's that little gap. And that all has to do with this. And that's all I'm going to say in this particular video, because we're going to save that for another video. And I am going to write a note here that there is crossover distortion. Okay, we now know how this amplifier performs, at least a rough idea of it. That's really all we need to know right now. You can go into all kinds of elaborate tests. So I would say this is a pretty good amplifier. And you could really say that you could put a transformer on it and use it as is, and most people would be very happy with the way it performs. A couple videos ago you heard me play some music through it, and it really didn't sound bad. It did pretty well. So in my opinion, as it sits, this is an acceptable amplifier. So that's a wrap for this video. We now know how this thing performs, and moving forward, any changes we make, we can go back and compare to what we were getting here. So hopefully that gives us some information to get some idea of how making changes on this is going to improve or not improve this amplifier. So until that time, I wish you all peace, joy, happiness, and good health in your lives. We'll see you again real soon for the next part. Stay well, everybody. Bye-bye.